Hello everyone, we are Group 1 and this is our presentation for the term paper Improving 2D Features Representations by 3D Aware Fine Tuning. This work tackles a key limitation in the current visual foundation models, their understanding of the 3D structure. We'll explore why this is a challenge and how this paper proposes to address it by injecting 3D awareness into 2D models. Now, what's the core problem? Current state of the art visual foundation models have shown incredible capabilities. However, they are largely trained on massive datasets of 2D images. While this has led to significant advancements, it also means that these models often lack a deep understanding of the 3D world. Think about it. A 2D image is just a flat projection of our rich 3D environment, and in that projection, explicit 3D information is lost. This can lead to issues where models don't produce view consistent features when observing from the same object from different angles. Humans, on the other hand, naturally perceive and reason about the underlying 3D structure of what we see. This gap is what the paper aims to bridge. Now, this brings us to the core proposal of the paper, 3D aware fine tuning. The central question is, can we enhance large-scale 2D models by giving them a better sense of 3D structure? The authors propose a novel two-stage approach to achieve this. First, they take existing 2D features and from the foundation models and lift them to a 3D representation. Crucially, they use an efficient 3D Gaussian representation for this, which allows them to consolidate information from multiple views and create what they call 3D aware fine tuning. In the second stage, these generated 3D aware features are used to tune the original 2D foundation model. The hypothesis is that this process will transfer 3D awareness into the 2D model, leading to richer and more robust features that improve performance on tasks that benefit from a 3D understanding. Some examples of these tasks can be semantic segmentation and depth estimation. Now, before diving into the paper's method in deep, it's important to understand the landscape of related research. Firstly, there's the vast field of 2D representation learning. We have seen remarkable progress here, particularly with the self-supervised learning techniques that can learn powerful visual features without needing manually labeled data. These include methods like pretext tasks, where the model solves an artificial task like image rotation prediction. Contrastive learning, where it learns by comparing different image views. And more recently, masked image modeling, which has proven very scalable. However, a common thread across many of these powerful 2D methods is the reliance purely on the 2D image data, meaning they often don't inherently learn our 3D structure of the world. This is exactly what our paper seeks to address by injecting the missing 3D awareness. Secondly, we look at the areas of distinct feature fusion fields. Neural radiance fields, or NERFs for short, have revolutionized the 3D scene representation, allowing for high quality 3D reconstruction and the ability to generate new views of a scene. Building on this, researchers have started distilling features from pre-trained 2D models into these 3D fields, enabling impressive zero-shot 3D understanding capabilities without needing new labels. Now, while our paper shares inspiration with these models by also distilling 2D features into 3D representation, its core objective is different. Instead of solely using these 3D features for directly 3D tasks, this paper aims to use the features rendered from this 3D representation to go back and enhance the original 2D feature extractor itself. The key technical choice here is the use of the recent and very efficient 3D Gaussian splatting technique to represent these 3D features. This is a crucial point as it allows for fast optimization and real-time rendering, which is vital for their fine-tuning pipeline. More importantly, the authors state that this is the first work to show these kinds of semantically rich 3D representations and can be used to effectively fine-tune and improve 2D foundation models. Finally, there's this specific area of injecting 3D priors directly into 2D representation learning. While much work has been focused on lifting 2D features into 3D, less has explored the reverse. Some methods like Pry 3D have used geometric constraints from depth data, and others have adapted masked autoencoders inspired methods for learning the 3D priors. The distinction of the current paper lies in its approach. Many of these prior methods require designing specific pretest tasks and often involve pre-training and 2D backbone model from scratch, pre-training a 2D backbone model from scratch or extensively training it on large amounts of dataset. In contrast, this work focuses on taking already powerful pre-trained 2D foundation models like Dino, Clip, ME, etc. and fine-tune them to imbue them with 3D awareness using 3D Gaussian features we just discussed. As you can see, the research paper has also given us metrics on how their 3D feature space have been embedded into popular vision models like Dino, Dino V2, Clip, Det, etc. This makes the approach more computationally friendly and applicable to a wider range of existing models. So, we have seen the motivation and the related work. A critical component that makes this paper's approach feasible and efficient is its choice of the 3D representation of those quote-unquote lifted 2D features. As mentioned, they leverage a technique called 3D Gaussian splatting. Why is this important? Gaussian splatting is known for its ability to be optimized very quickly and crucially. This efficiency is paramount because for the fine-tuning stage, the model needs to generate these 3D aware feature maps as training targets, and doing so rapidly is the key. It's this technique that effectively allows them to bridge the 2D and 3D worlds for their fine-tuning strategy. Now, I'll use a software called post-shot beta. It's still in its development stage, but we can use Gaussian splatting by giving it different images from different views of a single object, and it will generate a 3D interactable environment using Gaussian splatting technique. As you can see, here is our reference image. We gave it along with 2 or 3 more from different angles, and this has created a Gaussian splatting and a 3D environment to interact with the image. You can see very clearly even the shadows and the reflections from the surfaces are very clearly preserved. This will help in fine tuning the 2D to 3D images models. Also, we can see here the places where the information was lacking, the side here or the back, which the information of which we did not give into the software, is replaced permanently by black Gaussians. But here on the border we can see smaller lines, circles. If we zoom in, we can see these are all small Gaussians. One example would be this one. These are all small Gaussians which, when given proper information, combine together to form the meaningful image, as we can see. Now, we'll be explaining 3D Gaussian splatting briefly.
So before we explain the method developed in the paper, let's talk about Gaussian splatting since we use it to lift our 2D images into 3-dimensional space. Gaussian splatting is a unique way of representing scenes in 3D space, where instead of using polygons and triangles in a scene, we use millions of tiny Gaussian blobs. These blobs then blend smoothly, producing a continuous output that then resembles our original ground truth image. This way, we represent scenes not as discrete surfaces, but as a collection of overlapping semi-transparent blobs that then give us much greater detail than normal triangles and polygons would have given us. There are numerous reasons as to why the authors chose Gaussian splatting instead of adopting the normal polygon triangle methods. The most important reason is that Gaussian splatting is very fast. It offers close to real-time speeds even with its computational complexity. This was essential because the core of the pipeline is actually iterative. So the representation needed to have a fast rendering mechanism for it to be able to run multiple times in a loop. The second reason comes from the fact that Gaussian splatting at its heart is an optimization problem. It's going to initialize with a point cloud which comes from our ground truth images, but to guess the parameters for the millions of Gaussians, including the scale, the rotation, the color, we iteratively refine our configuration. So to be able to perform this optimization as fast as possible, the equations being differentiable is a really useful property. Gaussian splatting also offers extreme levels of details in its rendering with high speed. Like in this scene here, there's a really good amount of detail even in like the brick textures, the lighting, the reflections, the shadows, all of them are captured really accurately. Now let's look at a bit of the math behind the 3D Gaussians and how they're represented in equations. For every Gaussian in our scene, we have 5 parameters for the actual Gaussian distribution itself, and the last parameter f is a learnable parameter for storing our 2D distilled vectors in 3D space. The mean vector marks the center of the Gaussian, which is where the point cloud would be initialized when you input the image. S is a scaling matrix for the x, y, and z axis, so it's a diagonal matrix. Similarly, R is the 3D rotation matrix defining the rotation across the 3D space, and S and R together define the covariance matrix of our Gaussian. And as usual, alpha is a number between 0 and 1 for the opacity value, and SH is a vector that holds the spectral harmonic coefficients, which is really just a fancy way of denoting the color values for the tiny Gaussians. So with the notations out of the way, we can now transition into how the authors leverage this representation to inject 3D awareness into 2D vision models.
Alright, so let me take you through the main idea behind the method in this paper. It's actually quite elegant. The authors start with a simple observation, and the observation being modern 2D vision models like DynoV2 are super powerful, but they don't really understand 3D. They see textures, edges, and objects, but not necessarily the structure of the world in 3 dimensions. Now, the major big question is, can we take these great 2D models and gently nudge them toward 3D awareness without changing their architecture or retraining them from scratch? So that's what this paper sets out to do. And to pull it off, they design a two-stage process. So first, they take the 2D features and lift them into 3D. And in the second stage, they use the 3D features to fine-tune the original 2D model. Now, let's start with the first stage, lifting into 3D. So we have got various images. Actually, these are multi-view images of a same scene taken from different angles. We pass each of these images through a pre-trained model like the Dino V2, and we get this rich 2D feature maps as you can see here. So now, this is the cool part. They reconstruct the scene as a collection of 3D Gaussians. These are like soft blobs floating in 3D space, and each one stores their own information. It's the information are where it is, how big it is, how it rotates, and how it looks from different views. And crucially, a learnable feature vector which they call f. So now the f vector is kept low dimensional to keep things efficient. Think like 16 or 32 values. But later on, they pass it through a small CNN decoder and project it back to a higher dimensional space, closer to what DynoView originally outputs. And so now we got a set of Gaussians, as we can see here. Now we can render both RGB images and feature maps from this Gaussian image. Now we need to train these Gaussians. So we uses two types of loss. So here the first loss is actually the RGB loss, which is represented by LC. And it just says, can we render the image back accurately? Second, there's a feature loss, which is the LF. It says, when I render the feature map from this 3D structure, does it match what Dino V2 gave me in the first place? Now here's a key detail. They only update the feature vector F using the feature loss as represented by LF. The position and the shape of the Gaussians are updated only based on the RGB loss. So this is all for the stage 1. Now we have built a 3D aware feature rendering system from scratch. Now moving on to stage 2. This is where we use the system to fine tune the original 2D model. Here's an idea. Now that we can render 3D aware feature maps from the Gaussians, why not use them as supervision? So for every training image, we are rendering here you can see the corresponding feature maps using the 3D Gaussians and then compare it to what the 2D model, that is the Dino V2 model, produces. We compute that loss and then we update the Dino V2 model. Here we can see that the loss is being computed and the Dino V2 model is being updated. We don't touch the Gaussians in, neither we do change the decoder. We are softly steering the 2D model toward something that aligns with the 3D aware world. And the best part of all this process is that the fine tuning we are doing is actually very light. It runs in just one epoch. It uses a small learning rate. There are no new modules or networks introduced. The model stays clean and lean. Finally, now we are in the last stage. Here, we evaluate the improved model. We are evaluating it on two tasks. First is the semantic segmentation, and the next one is depth estimation. They keep it simple. Take the features from the fine-tuned model and slap a linear classifier on top. Oh, and in a neat trick, they actually concatenate the original features with the fine-tuned ones. That way, the model retains all its general purpose knowledge while also gaining a sense of 3D. Yeah. So to wrap up, what I love about this method is how it threads the needle. It respects the strength of existing 2D models, adds in 3D awareness in a meaningful way, and does it all with a minimum fuss. So now I will hand it over to my friend to walk us through the more technical nuts and bolts of how this all works under the hood.
Thanks. So now that we have seen the big picture, let's zoom in onto the more technical details and know why do they actually make sense. First of all, why did we choose 3D Gaussians instead of using something like NERFs or voxel grids? It is because Gaussians are lightweight. They render very quickly, but most importantly, they are differentiable. Does this ring a bell? Yes, it means that we can train them end to end. Each Gaussian stores a few things: a location in the 3D space, a rotation, a scale, view dependent color, and most importantly, the learnable feature vector F that we just mentioned. Now, when you render a view, multiple Gaussians might overlap on the same pixel. So naturally, the question arises, how do we decide what we see there? Now here, we use the technique of alpha composting. Don't worry, only the term is difficult. It's just a fancy way of saying that blend the contribution of each Gaussian based on their own transparency and depth. And when it comes to features, they use the same composting weights to blend the F vectors, only after decoding them into a higher dimensional space. But don't you think that this puts us into another problem? Yes, you are correct. The problem is of memory. You cannot store a full 384 dimensional feature vector per Gaussian, and especially not when there are thousands of Gaussians. So instead, what we do is we store a small vector and expand it at the render time. A very smart trade-off, I must say. Now moving on to the training part. The RGB loss is very straightforward. By the way, this LC over here, this is the RGB loss. It is very straightforward. It is just an L2 loss between this rendered RGB image and the ground truth image. Similar is the case for the feature loss, this one. It is also an L2 loss between the rendered feature map and the ground truth feature map. Mind it, this ground truth feature map is actually the Dino V2's output, the model that we just mentioned before. And again, just to emphasize, the geometry, the 3D position, the scale, and all such things, they get updated using this RGB loss. And the feature vector f, this feature vector f, this gets updated through this feature loss. Now, why do we separate this? What's the use? This separation keeps this optimization stable, and that's very important for the model to run effectively. And now let's move on to the last stage, that is the fine tuning stage. In this stage, we freeze all these things. Now, what do I mean by all these things? It is essentially the Gaussians, the decoder, and the whole of the 3D system. For now, their part is done. Now they only serve as a teacher. Now the question arises, to whom do they teach? They teach the 2D model. What happens over here is we render the feature maps from the 3D aware system and then fine tune the original 2D model so that it can align with them. Now what makes it work so well? It is because the rendered features are cross-view consistent. Once again, a fancy term. What it means is that they have seen the object from multiple angles. And so now the 2D model starts learning to encode not just the textures but also the structure. And that's what we wanted. And yeah, one important thing, all of this happens in one single epoch, which means a very little compute. So therefore, all the Gaussians and decoders can now even sit in a CPU memory. And if you use GPU memory, it's the training batches run very fast. In the end, when they test the model using, we say, simple linear classifiers, the performance improves drastically, especially on tasks of segmentation and depth. It is because these tasks have require spatial understanding at the most, and they are careful to preserve generality too. And it is done by combining the original and the fine-tuned features. All in all, I think it's a really clever way to give 2D models a kind of 3D intuition without even rewriting the whole system.
Experiments and results. This segment will detail the experiments conducted and the results obtained, which collectively demonstrate the effectiveness and generalizability of the proposed 3D aware fine-tuning methodology. As a basic summary, the data sets used for training was ScanNet++, and evaluation was done on the ScanNet++ validation set, ScanNet, NYU-V2 and out-of-domain datasets such as ADE20K and Kitty. The evaluation was performed on two downstream tasks, mainly semantic segmentation and depth estimation. Now, datasets utilized. For training the 3D feature Gaussians, the ScanNet++ dataset was employed. This large-scale dataset comprises 3D indoor scenes, offering high-resolution laser scans, registered DSLR images, and RGB depth streams from mobile phones, thereby providing rich 3D structural information crucial for learning. Evaluation involved the following datasets: ScanNet++, ScanNet, NYU. So NYU-V2 is a dataset comprised of video sequences from a variety of indoor scenes as recorded by the RGB and depth camera from Microsoft Kinect. Out-of-domain datasets included ADE20K, which is 20,000 images with over 150 semantic categories, including indoor and outdoor scenes as segmented maps. Pascal Walk, used for object detection and segmentation, including 11,000 images with 150 classes. And Kitty, which is depth maps, stereo images, and segmentation maps of outdoor settings obtained using a LiDAR attached to a car. So for evaluation, the fine-tuned features were assessed on two primary 2D computer vision tasks. One, semantic segmentation. This task involved the classification of each pixel within an image into a predefined semantic category such as chair, table, or wall. The evaluation method, a linear layer was trained to predict class logits using patch tokens from the feature extractor. These logits were then upsampled to fit the higher resolution image that we wish to segment. 2. Depth estimation. This task entailed predicting the distance of each pixel from the camera, effectively generating a depth map of the scene. The evaluation method was by breaking up the range of depth predictions into 256 bins and concatenating a class token at the end of the patch tokens. The linear layer could be trained to predict which bin the pixel's depth would lie in. Now, the base 2D feature extractor primarily utilized was Dino V2, a robust self-supervised vision model. Its performance was systematically evaluated both prior to and following the application of the 3D aware fine-tuning. Now, the performance on within domain. So, initial evaluations were conducted on datasets possessing a similar data distribution to the training data, specifically indoor scenes. For semantic segmentation, across ScanNet++, NYU V2, and ScanNet datasets, the 3D aware features consistently yielded improved performance for Dino V2. For instance, on ScanNet++, a notable gain of 2.6% in mean intersection over union was observed. This is a standard metric for segmentation accuracy. In terms of depth estimation, concurrently for depth estimation, the enhanced features consistently demonstrated a reduction in the root mean square error and indicating increased accuracy in depth predictions.
Now, talking about qualitative observations, the visual results provided compelling evidence of the method's benefits, primarily manifesting in two distinct aspects: enhanced segmentation and depth in homogeneous or textureless regions. Standard 2D models often encounter difficulties in accurately segmenting or estimating depth in uniform areas such as plain walls, due to a scarcity of explicit visual cues. However, through the aggregation of features from multiple views in a 3D representation, the model acquires a more comprehensive scene understanding. This multi-view awareness, subsequently transferred during the fine-tuning process, contributes to denoising predictions in these challenging regions. The second one being improved prediction of fine-grained details. The fine-tuned features exhibited superior capability in capturing intricate details, exemplified by the thin legs of chairs or tables. This is attributed to the training of the Gaussian's geometric properties, which are supervised by RGB color information. This supervision facilitates the learning of detailed 3D structures and the rendering of high-resolution feature maps, enabling the fine-tuned model to estimate more precise, fine-grained features of the objects.
Next, out-of-domain evaluation or generalization. A critical assessment of any machine learning methodology involves its capacity to generalize to previously unseen data. The 3D aware fine-tuning, trained exclusively on ScanNet++ that included only indoor scenes, was subsequently evaluated on datasets exhibiting significant domain shifts. including 1 ADE20 and Pascal walk. These datasets are general semantic segmentation benchmarks encompassing a diverse array of indoor and outdoor scenes as well as objects. Second is Kitty. This is an outdoor dataset specifically focused on urban driving environments, representing a substantial divergence from the indoor training data. Clearly, the data from all of these datasets is very different from the training dataset that was a part of ScanNet++. The results obtained were significant. For semantic segmentation, even in the presence of a considerable domain gap, the incorporation of 3D aware features resulted in discernible gains in MIOU on ADE20K, that is a 1.6% increase, and Pascal walk, that is a 1.2% increase. For depth estimation, on the outdoor Kitty dataset, the 3D aware features contributed to a reduction in the RMSE for depth estimation. Uh, these findings unequivocally demonstrate the transferability of the learned 3D awareness across diverse datasets and environmental contexts. Qualitatively, similar improvements were observed, characterized by reduced segmentation noise and enhanced capture of detailed structures, even for objects such as bicycles, animals, trees, and buildings. Clearly, these objects were not part of the initial dataset. Generalization to other vision models. To further substantiate the universality of the proposed method, the researchers applied their 3D aware fine tuning to additional prominent 2D vision models, including Dino V2 Reg, CLIP, MAE, and Diet 3. The consistent improvement in performance across all of these models for both semantic segmentation and depth estimation tasks underscores the broad applicability for the approach.
Now, on to ablation studies and analysis. The paper also includes comprehensive ablation studies, which are experimental designs aimed at elucidating the individual contributions of various components within the proposed methodology. One of them being feature dimension of each Gaussian. Investigations revealed that increasing the feature dimension from 32 to 64 yielded improved performance, albeit with an acceptable increase in memory consumption and training time. This observation confirms the inherent trade-off between computational efficiency and feature richness. The next is feature assembly strategy. Different strategies for combining the fine-tuned features with the original Dino V2 features were explored, including simple addition, linear fusion, and concatenation. The results indicated that simple concatenation was the most effective strategy, successfully integrating the learned 3D awareness while preserving the original model's generalization capabilities. This finding reinforces the complementary nature of the 3D aware features. Next up is fine-tuning epochs. A noteworthy discovery was that a single epoch of fine-tuning was sufficient to transfer the 3D awareness. Extending this number, in some instances, negatively impacted the model's generalization ability, highlighting the efficiency of the fine-tuning strategy. And finally, fine-tuning versus adapter. A comparison between direct fine-tuning and the use of an adapter, which is a small auxiliary network integrated with the frozen Dino V2 features, was also conducted. While the adapter achieved comparable performance, it necessitated a longer training duration. Consequently, the direct fine-tuning approach was favored for its simplicity and efficiency. Now, finally, to give you a final summary of what's happening, this paper presents a powerful and efficient methodology for injecting 3D awareness into 2D visual foundation models. By transforming 2D features into a 3D Gaussian representation and subsequently utilizing these rendered 3D aware features to fine tune the 2D model, consistent and notable improvements are achieved in downstream tasks such as semantic segmentation and depth estimation. The methods demonstrated ability to generalize across diverse datasets, including out-of-domain scenarios and other vision transformers, is particularly significant. This research initiates promising avenues for future inquiry, encouraging the broader scientific community to investigate how the integration of 3D understanding can further augment the capabilities of 2D foundation models. This work represents a crucial step towards equipping artificial intelligence systems with a rich, inherent perception of the three-dimensional structure of the world rather than merely processing flat images. Thank you.